And today I'm going to talk a little bit about a recent study that a few colleagues here in the Watershed SFA were also a part of, which kind of compares and contrasts hydroclimatic change between, say, places like California and Chile, which are located in what's called the American Cordillera. But first, I just want to, again, thank Ken and everyone on the call here for showing up and listening today. To give you a little mental map of my presentation, first I want to just build a case for why mountains really are unique and have an outsized influence on human systems. Maybe a mute point to this group, but to others that I've given this talk to, I think beneficial. Provide a literature review on the major drivers of hydroclimatic processes in mountain regions, particularly those that have an outsized influence on things like water availability and reliability, such as snowpack and atmospheric rivers, which are kind of the center of most of my research these days. Highlight some of our recent research, which highlights how mountain hydroclimate processes could change under different levels of warming, and convey what that means downstream wise for water managers and maybe the planning horizon surrounding adaptation to these changes. And at the end of the talk, I'll, again, like I was saying, discuss a recent paper we published that spans all the aforementioned topics, compare and contrast kind of hydroclimatic change between geographic regions that share commonalities, namely in the mid-latitudes, the American Cordillera. And I just wanted to mention that a lot of this work is funded by two DOE projects, the Hyperfacets project, which is focused on kind of the usability of climate information, where scientists like myself get to engage with actual practicing water managers throughout the continental US and kind of do co-production in a way of our science. And then the other is the Cascade SFA, which is more basic science and is focused on climate extremes. And so that's where I get to play around with kind of wonkier model things and tracking atmospheric rivers and the like. So I feel pretty fortunate I have these two projects that I get to interact with. And so first of all, I just wanted to highlight that the importance in kind of mountains. In a sense, they're nature's dams and water towers. And they comprise about 12% of the global land area outside of Antarctica. And before I started working in kind of mountain research over the last few years, I didn't realize that we're still debating on what a mountain is. And so you'll see in this 2017 paper here, Christian Kerner had this really nice paper about how to define a mountain, intercomparing with other mountain masks around the world. But it's basically his definition, which I think is one of the most compelling, is that mountains comprise kind of this black area around the world. And so the American Cordillera, which we'll talk about today, kind of stretches from the southern tip of Patagonia in Chile and Argentina all the way up to Alaska. And it's just this kind of mega chain of mountain ranges that's kind of unprecedented latitudinally across the world. But to kind of hit home why they're nature's dams and water towers, I think there's a nice paper by Emerziel and also Huss, which is more of a review paper in 2017, highlighting what's called this water tower index, or WTI. And so basically they came up with a methodology to highlight how much a given region within this within this Kerner mountain mask regions, how these populations are dependent on water derived directly from mountains. And so this is a 0 to 1 index. So there's a lot of assumptions made, but in places where there's a 1, such as the Tibetan Plateau, and then outside of the Tibetan Plateau, places like southern Chile and places like Colorado and the Colorado Rockies, Sierra Nevada, are some of the regions where you see higher dependence from mountain-derived water. And so there's an estimate that about 25 to 50% of the world's population is dependent on mountain-derived water through things like snow melt or glacial melt. And another thing that I like to highlight about mountains is that they're almost like a compact Earth, right? They bring starkly distinct climate zones into close proximity with one another. And in a way, this leads to kind of some of the most species-rich places in the world, biodiversity hotspots. And so in this paper by Robeck here, he's highlighting that in this red region here, which is parts of the northern Andes, the northern Chilean and into the Peruvian Andes, roughly half of the world's temperature, precipitation, climate space, which is kind of shown here. You might have heard of the Köppen-Geiger kind of space, but this red region encapsulates all of the 50% of the mean annual temperature and annual precipitation that's possible across the planet. So in a way, mountains are like moving up slope in mountains, is equivalent to moving thousands of meters, which is roughly equivalent to moving thousands of kilometers from the equator to the poles, in a sense. So there are these magnificent, just compact earths. And so I mentioned earlier, but I just want to highlight again what the word American Cordillera means, because I didn't know before starting this research, but I think it's a really nice term. And again, it's this long series of mountains that stretches all the way from Alaska, which is not shown here, all the way down to the tip of Patagonia in Chile and Argentina. And it's one of the longest series of mountains in the world, latitudinally. And I've just taken some photos here on different travels, and you can see that, you know, a lot of places around the American Cordillera are places where large seasonal snowpacks build. They're dependent on atmospheric rivers for a large amount of their precipitation each year. And a lot of the communities within the American Cordillera are also dependent on both atmospheric river-derived water and snowmelt in the spring into early summer from snowpacks. And so just to kind of build the case on, you know, what an atmospheric river is. So an atmospheric river is kind of a term that's come about in the last decade. But basically, they're large filamentary structures of water vapor that transport about 90% of the water vapor from the equator to the poles. On the left here is a recent, really nice, I think, animation of the recent Pineapple Express, which is a flavor of atmospheric river that made landfall in California and produced some flooding actually in the lower San Joaquin Basin. But these atmospheric rivers are equivalent to, you know, 7 to 15 Mississippi rivers worth of water. They're often tracked using what's called integrated vapor transport. So the idea is that if you take all of the column of atmosphere and you condense all the water out, IVT is telling you how fast that amount of water is moving in any given time and direction. And so on the right here, I'm just showing that in these two mid-latitude regions of the American Cordillera, so Chile on the right, Western US on the left, there's a lot of tracks of atmospheric rivers shown. And so you can see that they drive a lot of the precipitation totals in these regions. And so this is kind of shown also in observation studies in situ locations, both in the Western US and in Chile on the right. And basically in large parts of, especially California, we get about 50% of our annual precipitation in a matter of days. I think there's been a recent updated study that said that we get it in a matter of hours, especially in Southern California. But in about 5 to 15 days, we get 50% of all of our water, which is pretty remarkable. And in Chile, again, this is also the case where ARs are associated with about 40 to 60% of the annual precipitation, so even more. And a really important aspect of these storms is that they are derived from the tropics or equator. And so, and they move predominantly along the ocean surface. So they don't have a lot of time to cool over, say, the Western United States or something. So when they make landfall, they produce much of the precipitation at or near freezing. And so the figure on the right here is showing the fraction of precipitation that falls at or near freezing. And so places in red, for example, in the Sierra Nevada, the Cascades, and even portions of, say, Idaho or other places, about 40% of the precipitation falls around that freezing. So you can kind of think with a warming world, atmospheric rivers are going to get kind of bumped up in terms of intensity through the Clausius-Clapeyron relationship, and more of their precipitation might start to fall as rain rather than snow. And so there's a really important connection between atmospheric river variability and their temperature and seasonal snowpacks in these two mid-latitude regions of the American Cordillera. And so because we get a lot of our precipitation and especially in California in 5 to 15 days as a matter of weeks, we hope that some of this is deposited as snow in the Western US. And so in this review paper that Eric and I led a couple of years ago, we just wanted to highlight kind of how seasonal snowpacks really shape water supply in the West, and how we've built this assumption of this that we'll have an abundant snowpack kind of indefinitely, and built our kind of management infrastructure with that in mind. And so on the right here, we're seeing the kind of water supply centers throughout the Western United States. The seasonal snowpack is underlaid as kind of a map here of, I don't know why there was a video playing there, sorry about that. The seasonal snowpacks, kind of the median snowpack, is shown underlain in blue, and all of the kind of water supply infrastructure are shown overlaid on top. Canal systems and rivers are shown in blue and red. And so what you can see is that a lot of our infrastructure in the West, and I don't have a comparable plot for Chile, but I assume the same thing is kind of there too, that we kind of move water where and when it's needed from the mountain systems where we get a lot of the seasonal snow to demand centers, which are shown on the right, which is things like hydropower facilities are, also taking some of this water. But a lot of these dots are the agricultural users of water or urban centers. And so just to kind of zoom in here, I gave this talk to a few California focused people in the last few weeks, but I think folks here in Colorado will also appreciate this, is that this is kind of looking at how much snowpack contributes to surface water supply relative to our largest surface water infrastructure in California. And this is work done by Mike Dettinger and Mike Anderson, the state climatologist. And so on the left here, this is a time series from 1970 to 2020. The light blue regions here are showing the kind of 148 reservoirs, smaller-ish reservoirs throughout the state. And then the dark blue are the larger reservoirs. And then put on top is the amount of April 1st snowpack storage that's provided by snow. And so snowpack roughly doubles our natural storage. It provides about 17 million acre feet of storage, and that's roughly equivalent to 5 Oroville dams worth of water. So it's a pretty large amount of water, and provides us with water during a time in which we really need it. And just to kind of hit home that there is a really close relationship between atmospheric river variability and snowpack variability. On the right here, this is California snowpack derived from ARs from 1998 to 2011, and then the mean is shown on the far right. Green bars are highlighting the amount of SWE contributed by atmospheric rivers. So about 37% of California snowpack is derived from atmospheric rivers. And then in Chile, this is even more so. So this is the Chilean snowpack from ARs, and the kind of darker gray is the AR contributed snow water equivalent from ARs, and so it's about 55%. So again, there's this really important interaction between atmospheric river variability and peak SWE. And just keep in mind that in a warming world, these ARs are going to start to produce more rain, less snow, potentially lead to also more flooding. But because I knew that I was talking to more Colorado folks here, I just wanted to point to Mike Dettinger's ongoing work where he updates these really nice plots that are kind of showing the subseasonal variability of snowpack storage and reservoir storage. And so what's shown here are the reservoirs upstream of Lake Powell. The average upstream reservoir storage is shown in this kind of light blue, and then superimposed on top is the snowpack storage. And then the red line here, there's a lot going on, I know, but this red line is showing snowpack storage plus reservoir storage plus snowpack. And so what's shown here is that the upstream reservoirs are a lot lower than is normal, but we've been having a healthy snowpack, as I believe Andrew was his name earlier was showing for the state of Colorado. You're above normal at this point, about 130%. So I just wanted to highlight that in Colorado, the relationship between snowpack storage and reservoir storage is even larger than, say, in California. And then, we'll see in a warming world too, if there's as much of a one-to-one relationship of snowmelt from that snowpack storage actually making it to reservoirs, which is kind of ongoing area of research, I would say. Okay, so now to kind of put the trends of how April's first snow water equivalent is changing into context, I think this plot by Moat and Sharp in 2016 is really compelling in that it's showing all of the snowtell sites around the Western United States. And it basically what they're saying from the 1950s to about 2016, there's a 90% of these stations are highlighting a 23% decline on average of snow water storage. The red circles indicate decreasing trends of April 1st storage. Blues indicate increasing trends, and then the size of the circle is the size of the trend or percent change. And so predominantly throughout the West, there's been a lot of snow loss over the last, say, 70 years or 80 years. I couldn't find a comparable for Chile, but they're able to use kind of dry season snow cover as a proxy for maybe April 1st snow change, or not April 1st, peak SWE snow change. And what they've shown is that dry season snow cover throughout much of the regions where they need water supply from snowpack, because they have a lot of their population centers there, which are shown on the right. There's been about a 15% decline per decade of dry season snow cover in kind of the Andean regions shown here. And what's unique about Chile relative to the Western United States too, from an infrastructure standpoint, is that 1/3 of their whole population lives in Santiago, Chile, its capital city. But the country itself spans, in essence, kind of the distance from, say, Bogota, Colombia to, I think, New York in terms of latitude. And then the width of the country is about from driving from LA to Las Vegas. So it's this very extremely long country that building infrastructure for where they get a lot of their precipitation from, say, atmospheric rivers, or they have a lot of water availability, a natural water availability from the south. It's really hard to build the canal systems and structures to capture water and then move it up north to Santiago. And so that makes this region really dependent on very few mountain basins like the Maipo Basin for their water supply in the summertime. And those basins, as shown on the left here, have been experiencing considerable snow change over the last few decades. And so to kind of put into context what might we expect, because previous slide was observed trends, now what we might expect for, say, the Western United States moving forward. Eric and I, in this review study, did a literature synopsis of about 18 studies. So we looked over the peer review. We highlighted the different methods as shown by these little symbols here, what method those were. And then we tried to kind of put into context across the Western United States and then also individual mountain ranges. I would just, point you to that study to look at, say, the Colorado Rockies or whatever mountain range is your favorite. But we tried to highlight what the potential SWE loss would be over these, early century, mid-century, end century kind of perspectives. And what we're seeing is that we have the models are projecting about a comparable change in snow water equivalent as we've seen in the observed record by about 2050, about a 35% loss out to 2075. And then upwards of 50 to 60% by 2100. So the projections are highlighting that this trend should continue, maybe even amplify by end century if emission scenarios continue. And there's not necessarily a literature review equivalent in Chile, but colleagues and friends of mine led a study in 2021 using a single model called the variable resolution CESM model, and we were able to project how the Chilean cryosphere might also change in a warmer world. And I'd highlight or encourage you to read this paper as well. But we also show a comparable kind of decline, earlier timing in peak snow water equivalent, and a decrease in the volume across most of the regions highlighted here, especially in regions where there's high population centers or places where there's evidence, even in the historical period of enhanced drought occurring, for example, in this region here in Chile, where Chiloé is. And so I would just, again, point you to that paper for more details. So from a water supply implications perspective, these are pretty simplified curves, but I think they're nice in conveying kind of how this becomes a water supply challenge, both from a snowpack perspective first, and then I'll show from an atmospheric river perspective in a kind of changing climate. So currently, in our historical perspective, we get a lot of our precipitation in the winter and kind of peaks around spring, and then water availability or water supply kind of decreases, whereas demand is kind of peaking in the summertime when agriculture most needs the water. And so there's this kind of mismatch between the peaks that snowpack really helps to provide kind of a bridge to. But in kind of a warmer world where there's less snow, so that water supply curve might shift lower and move further apart from one another. And so an earlier snowmelt can lead to less water availability and then even greater mismatch between when peak demand might occur. And so that could create even larger water shortages kind of in this perspective. And so talked a little bit about snowpack in a warmer world, and now I'll talk a little bit about atmospheric rivers. And so I thought it'd be timely to talk a little bit about the new atmospheric category scale. It's analogous to, say, the hurricane scale, where they try to rank atmospheric rivers based on their AR intensity, so the maximum IVT they reach during their lifetime, and their duration from 0 to, say, 3 days. And they rank them from 1 to 5. 1 and 2 ARs are primarily beneficial to water resource management, meaning that they provide kind of a steady amount of precipitation, don't cause a lot of flooding events. When you start getting into 3, 4, and 5, that's when you start to get into more of the hazardous kind of AR categories, where you have some of the most historically unprecedented flood events in California history, for example. And so on the left here is, again, that category scale. On the right is kind of historical flood damages associated with those atmospheric rivers and broken down by each of these categories. So just to hit home that there is a non-linear kind of relationship between flood damage losses and atmospheric river categories, where we've had about 11 category 5 AR events in the Western United States over the last 40 years. And they've produced considerable damages, upwards of billions of dollars. But as a whole, ARs have accounted for about 84% of all flood insured losses in the 11 Western US states. So pretty amazing stuff. And so again, the interactions between atmospheric rivers and snowpack are really important to note. AR conditions are kind of associated with 50% of the rain on snow events. And for example, in February 2017, and most likely in the coming days here in California, we'll see some, the effects of how rain on snow creates kind of flooding in kind of rural mountain communities in California. But in the matter of 50 days, we got an average year's runoff up above Lake Oroville in 2017, and so that led to, in part, this kind of almost catastrophe that happened in Oroville that could have potentially led to dam overtopping. So this kind of interaction between warming ARs, warming snowpacks, as we head into the next few decades, will be important to kind of research and monitor. And so in a study that we also led here at Berkeley Lab, we wanted to isolate how these atmospheric rivers and their character might change with different levels of warming. And so we used cutting edge kind of high resolution Earth system modeling approach to generate years and years and years of atmospheric rivers that make landfall in the Western United States at, say, pre-industrial warming levels on the first column here on the left, kind of present day warming in the second column here, and then 1.5, 2, and 3 degrees of warming associated with kind of the IPCC global warming levels that they're most interested at. On the first row here is kind of the return frequency of those category 1 and 2 ARs per year, so the mostly to primarily beneficial ARs. The kind of intermediate ARs where they're between hazardous and beneficial in the second row. And then the third row here is those extreme ARs, so the very hazardous ones that create a lot of flooding. And so you can kind of see that in a warmer world, as you warm, you can see that more and more of the category 3 and 4, 5 ARs start to make landfall more frequently, particularly in Oregon, parts of Northern California, and into Washington. And then on the right here, we wanted to translate how those subtle but important upticks in AR frequency changes play out in terms of flood damages perspective by using Tom Corringham's flood damages, historical flood damages data set, which was shown in the previous slide, to then sample within these model worlds of what we might expect on average. So you can see it in a 1 degree world and pre-industrial and present, maybe not a big difference in terms of annual average flood damages on the order of about $1 billion per year. But when you start to get to 1.5, 2 degrees, you start to double the flood damage potential. And then in a 3 degree world, you get up past 3 billion. And that's a direct relationship to the changes, particularly in category 4 and 5 AR events, as shown on the right, or on the left here. And so revisiting kind of this diagram again. So we showed snowpack previously, but now kind of overlaying what that might mean from an AR perspective when you have more rain, less snow, more precipitation coming in a even shorter window of time. And so that might lead to even more flood releases, as shown here. So we currently have to, sometimes in winter release for flood supply reasons or flood hazard reasons. But in a warmer world, we might see this accentuated water supply curve where you get even more rain, less snow in a more punctuated time that could lead to potentially even more flood releases, which then further impacts water demand later on into the summer and fall. And so all of that hopefully is building up for this kind of paper that I mentioned at the very beginning that's in Nature Climate Change called The Asymmetric Emergence of Low to No Snow in the Mid-Latitudes of the American Cordillera. And in this paper, we really had a few simple questions. And I think this paper really came about because when I was at UC Davis, I interacted with the Chilean community quite a lot. There's a lot of Chilean students that come. So we would have pisco sours in the backyard, talk about Chile and California in a real way. We often were kind of marveling at the fact that there's very similar cultures between California and, say, Chile. We have very similar climates. We both depend on atmospheric rivers, snowpack for water supply. And so we face a lot of the same challenges. So in this paper, I just really basically wanted to try to answer these two questions, which is, are we really mirror images of one another? Will our hydroclimates respond in the same way to climate change, or will it be asymmetric? And so again, just to highlight that the American Cordillera here is shown on the left. It's this black outline, in Chile and California are, part of that. And again, this is not really necessarily a new idea. I think that this has been this kind of asymmetry or symmetry between the mid-latitudes of the American Cordillera has been explored even back to Alexander von Humboldt days, where he would travel around the world and basically make these beautiful maps of the different mountains around the world and highlight their commonalities and differences and kind of where vegetation starts to arise and go away where the snow line arises. He also coined the term isotherms to connect very distinct mountain regions around the world to one another, or even climate regions, I should say. And in academia, you can look in the kind of paleoecology literature, and you can see that there's studies that compared California and central Chile to one another. And they would often compare and contrast, precipitation and temperature, and how that might have given rise to similar ecology in the regions. And you also see this in the paleoclimate community, trying to understand if in different ice ages or hot Earths, how did kind of the two hemispheres respond to those different levels of warming. And also in the popular media, you also see this where the Seattle Times, for example, said Chile, our mirror image of our West Coast. Huffington Post, recently talked about Chilean wildfires offer a glimpse of climate risks in California and elsewhere. And in the Universidad de Chile, what Chile can learn from California's fight against the drought. So there's, potentially this information sharing that we can do and contrasting that I think is really important from a climate change perspective. And so in this paper, we kind of break down hydroclimatic change and differences or symmetries and asymmetries between these two regions in kind of, I would put, three kind of main ways. So first, we compare kind of the hypsometry of the two regions on the left, and that's just a fancy term for differences in elevation, distributions, freezing area, slope, aspect, and land cover. We also looked at things like the thermodynamic response and dynamical response to climate change or global warming. And so from an atmospheric river perspective, for example, we often use IVT to look at it. So that's what's shown on these diagrams. And so from a thermodynamics perspective, atmospheric rivers are thought to kind of increase in intensity due to the Clausius-Clapeyron relationship, where a warmer atmosphere can essentially hold more water vapor. But the dynamical response of climate change might offset some of that, and in different ways between these two regions, where a dynamical response will be a net negative decrease in thought kind of in the Western US, but in Chile, there's maybe important differences where it could actually enhance in certain regions and offset in some regions. So, changes in the general circulation, storm tracks, storm intensity, duration, frequency were some of the things we also evaluated slightly in this paper, or made conjectures about. And then also there's important cross-scale interactions where changes in precipitation intensity, duration, and frequency, and efficiency, rain, snow partitioning, runoff efficiency really interact. And so we got into that a little bit as well. But in order to do this work, we needed a model suite that we thought could be suited for this problem. And so recently in the Intergovernmental Panel on Climate Change, there's this new high-res MIP ensemble that was produced, and it stands for High Resolution Earth System Model Intercomparison Project. You can read more about the high-res MIP protocol and models that are available here in the QR code. But essentially, a lot of the Earth system modeling that is done through the IPCC has been stagnated at about 1 degree resolution. And so 1 degree resolution is shown on the left here for the American Cordillera. And then I zoomed in over Chile to really highlight that a 1 degree resolution model, which is roughly 111 kilometer grid boxes, really smooths out the topography of the Chilean portion of the American Cordillera. You don't get as much much of the valleys that are important in the model runs, and the coastline or whatnot kind of comes out into the sea. But as you're getting to some of these high resonant model resolutions at, say, a 1/4 degree resolution, which is 25-kilometer grid boxes, you start to see a lot more of the complex topography of South America start to appear. And also in the Western United States, you get more of these valley structures, the high kind of peaks of the Andes start to pop out. So I would make an argument that, from an American Cordillera perspective, maybe we're starting to get to the resolutions where we can start to answer some of these questions about symmetry and asymmetry to climate change and how that might affect the hydroclimates in these regions. So all of that is to say that of all of the high resonant models that are available, we had to down select. I believe there's about 20 or so of them. We had to down select because these ensembles are often produced by atmospheric scientists that don't care about snow or land surface processes. So they don't always output the variables, unfortunately. But of the models that did, we have 3 here. And so the basis of a lot of my work is using kind of the MRI model. And that's because another caveat of this is that the models ran from 1950 to 2050. And I'll show in the next few slides, that's when you start to see when this low to no snow emergence starts to really occur, is in the 2050s to 2075 time period. So fortunately, a lot of the models didn't simulate out to, say, 2100 when you can start to see that. But fortunately, the model that we did get, I think we got lucky in some respects in that it's equilibrium climate sensitivity, which is this benchmark that Earth system models often care about, because it's basically the idea of if you double the amount of CO2 into the model, what will be the level of warming associated with that? And so it's led to this debate on hot and cold models in the literature. But the MRI model is kind of equilibrium climate sensitivity is about 2.6 degrees. So it's kind of representative of the median, maybe equilibrium climate sensitivity across models. And then I won't show it today, but we did a thorough investigation of its historical performance for precipitation, temperature, snowpack, and then highlight some studies which show that MRI is a pretty skillful model in the Earth system modeling community. But again, a lot of the results are based on one model here that I'll show. So I just want to caveat that more work is needed. We need kind of more, maybe a larger ensemble of models to really see or get a signal to noise out of these results. But I'm just going to really caveat that these are all single model results that I'll be showing. But from a hypsometry perspective, so again, on the left here, we're taking kind of the latitudinal or longitudinal average at each latitude along the American Cordillera. The green line here is showing the average elevation along that American Cordillera kind of latitude band. And then in black is a digital elevation model at 4 kilometer of the average elevation. So you can see that at least the average elevation banding is starting to be represented well by this MRI model that I mentioned that is run at about 20 kilometer resolution. However, the maximum elevations and minimum elevations along the Cordillera are not necessarily exactly represented. You have regions where the high peaks are not necessarily represented, for example, here, and in other regions where the elevation is too high, so it's not getting the valleys. But on average, it is kind of representing the kind of hypsometry of this American Cordillera region. From a dynamical perspective, so I mentioned that changes in the circulation can influence the kind of jet stream, which then influences where and when atmospheric rivers can make landfall and whatnot. And so we did an analysis where we computed the annual mean meridional overturning mass stream function. It's kind of a fancy term of just saying how fast is the circulation going in the northern versus southern hemisphere. How fast is it overturning? And so in the northern hemisphere in blue here and southern hemisphere in green, you can see that from 1950 to about 2100, the southern hemisphere doesn't have a large change in the general circulation, indicating that maybe the response to climate change might be more influenced to thermodynamic effects rather than circulation changes. But in the northern hemisphere, you're seeing a general slowdown of the circulation. And although this is kind of controversial, there's a thought that maybe this will create a wavier jet stream, which could lead to a lot more variability, for example, in snowfall or precipitation. So the climate change response in the northern hemisphere will be shaped by both dynamical and thermodynamical changes. And so on the right here is just kind of the hemispheric difference between these two, just highlighting that there is this kind of asymmetry in circulation changes between the northern and southern hemisphere. From a thermodynamic perspective, so this is showing annual average surface temperature anomalies from 1950 to 2100. Again, blue is the northern hemisphere, the southern hemisphere is in green, and then on the right here is just regions within that American Cordillera mask. What you see is that in the northern hemisphere, average surface temperatures increase at a higher rate and end up at a higher warming level. And the idea there is that that's Arctic amplification, where the kind of Arctic through sea ice loss, snow cover changes, becomes more bare and has a lower reflectivity or albedo. So it can absorb more energy relative to the southern hemisphere, where say Antarctica is, or other regions where you might not lose that albedo. So in part, that's what we're seeing here. But even in the American Cordillera, you're seeing kind of a larger amount of warming and, interestingly, a lot more variability from year to year. So that might be related to the circulation changes that I was mentioning. And so the interactions between precipitation and temperature changes, we wanted to kind of highlight what that looks like across the American Cordillera. And so, and because snow is such an important indicator variable for water supply reliability, we thought we would use snow as kind of our indicator variable of change in these two kind of hydroclimates as well. So in the 2021 article that Eric and I led a few years ago, we coined this low to no snow definition, and then kind of put it into practice in a proof of concept way in this study. And so basically, just to step you through what that definition says, the whole idea behind that is that when we did a lot of the comparisons across studies, we found that they were using different metrics like seasonal mean snowpack change, or April 1st change, or peak SWE change, or you can think of all the different ways that we define snow change in climate science, or in hydrology and in atmospheric science. So we thought maybe we should coin a low to no snow definition that could be used anywhere geographically, and that could also be used across studies to more evenly compare apples to apples to one another. And so this low to no snow definition, basically you filter peak SWE in a given year into 10th percentile bins over, say, a long-term reference period. We chose 1950 to 2000, and that's to kind of properly sample 50 years of climate variability associated with differences in how ENSO might play out in any given year, and the teleconnection response to, say, Western US or Chilean hydroclimate. So anywho, we used a 50-year historical period, filtered peak SWE into 10th percentile bins from that. And then we define low to no snow to mean that peak SWE is less than or equal to the 30th percentile. And then to also account for the fact that snow loss from a single year isn't necessarily won't necessarily stress water management. It will be kind of the back-to-back years of low to no snow that really start to stress water management. So then we defined back-to-back 2-year period, 5-year period, and 10-year period, and built that into the low to no snow definition too. And those are called extreme, episodic, and persistent low to no snow conditions. And then we use logistic regression to kind of identify the date of emergence of when low to no snow might occur by identifying the first year for which the probability exceeds 0.5 or greater than a random chance of occurrence. And so to just kind of show this visually on the right, I think Hofmahler diagrams are a nice way of doing that. And again, these are going to be latitudinal transects that are shown on the Hofmahler here. And any given year that is kind of a high snow year above median will be in light blue to really dark blue. Those will be the high snowfall events. And then anywhere where you get into the lighter to darker reds, that's when you get into low to no snow. And so you can kind of visually see when you start to get to the date of emergence when low to no snow might become persistent, for example. And so this is derived from our single model run that I mentioned, the 20-kilometer MRI model. And you can see the also level of warming associated with different years as well. So at about 2050, there's 2.7 degrees of warming, and at 2100, 5.6 degrees is the assumption. And then just recreated these Hofmahler plots from 1950 to 2050 across all the different models that I could get snow water equivalent from, and the other variables that I'll show later on in the analysis. But the low resolution versions of these models are shown on the first row, and the high resolution models are shown on the bottom row. And again, what the take home here is that there's a lot of noise in the signal up until about 2050. So unfortunately, a lot of these simulations, as I mentioned, only ran out to 2050. But if they had run out to 2100, we could have used even more models to do our analysis. But I thought I'd just show them here to say that we also looked at different models and when they might start to show low to no snow emergence. But to kind of do this a little bit more formally, we isolated, as I was saying, with logistic regression, the low to no snow conditions from a date perspective and from a degrees to emergence perspective. And so on the first column here, this is showing the northern hemisphere date of emergence of low to no snow from an extreme, episodic, and persistent low to no snow perspective. So again, a back-to-back year, low to no snow, when does that become greater than a random chance of occurrence? 5-year period of low to no snow, 10-year period. And this is showing the northern hemisphere. And then on the bottom here is the southern hemisphere. And so what you can see is that in the southern hemisphere, the low to no snow emergence from an episodic or persistent perspective comes at about around 2050, whereas in the northern hemisphere, it's about 2070. What's interesting is that the amount of warming needed to reach this low to no snow emergence in the southern hemisphere is at a lower amount, about 1.5 to 1.8 degrees of warming, whereas in the northern hemisphere, it's about 2 to 3.5 degrees of warming. So the southern hemisphere is expected to reach low to no snow faster, and it just requires a little bit more warming than present day. And to kind of show these kind of Hofmahler plots now from a spatial perspective, and also because several reviewers gave us the comment that we should really put this MRI model into context. So we use the Cordex model. So it's an ensemble of regional climate model simulations over say North America and South America. And so we were able to leverage those to kind of compare and contrast how this single model result that we use from the HiResMap ensemble compares to this regional ensemble. And so what is shown is, again, these Hofmahler diagrams on the left from the MRI model and then Cordex. And then these are the spatial maps of changes over these large periods of time. So 2015 to 2050, peak sweep change, and then 2051 to 2099. And then again, from the NA Cordex perspective. And basically what's shown here is that the Cordex models are actually saying that low to no snow might emerge faster and faster than the MRI model is saying. So the MRI model results, which are the basis for a lot of this work, might actually be a conservative estimate of change relative to the others. And then we did this again for South America. Again, the Hofmahlers are on the left here with MRI at the top, Cordex on the bottom. And a similar story here where you see peak sweep changes that are pretty considerable. Uniquely in South America, though, there's large glacial fields. So you'll see this positive SWE anomaly, and that's, I think, model dependent. And, if they have glaciers in the model and whatnot, but predominantly throughout the Western US and in Chile by, 2050 to 2100, peak SWE changes are pretty considerable. If, again, we continue to emit carbon in the way that we have been in kind of this high emission scenario. And so in the next few slides, I'll kind of break down again, kind of the latitudinal change across other variables, not just snow or equivalent. So on the left here, I'm just highlighting one variable to kind of step you through what's here because they're kind of complicated figures. But latitude, absolute latitude is on the left here. Again, like the circulation change diagrams I showed before in thermodynamic, northern hemisphere is in blue, southern hemisphere is in green. The historical kind of absolute temperature is shown in dotted lines, and then the change after low to no snow emergence is shown in the darker lines. And then there's little lines here at the top to indicate the average change across latitude bands of temperature. And so basically what I wanted to show here is that from a historical climate perspective, the southern mid-latitudes kind of started a higher annual mean temperature. And so that little bit more warming pushes kind of the storm systems probably above freezing more often. And so that's why low to no snow emergence occurs earlier and at a little less warming level, because it already started at kind of an annual mean temperature that's higher than, say, in the Western United States. And so this is kind of also showing, similar to maybe what I showed earlier with the thermodynamic changes, Where on the right here, this is the change signal of temperature, where you get about 1.8 or 2 degrees of warming in the southern hemisphere, and about 4 degrees of warming in the northern hemisphere when low to no snow starts to emerge. Now looking at a precipitation standpoint here, and then snowfall fraction standpoint. So what's interesting is that even in the historical period, the Western United States, or the northern mid-latitudes, produce less annual total precipitation than in the southern hemisphere, but latitudinally it's a lot more consistent than in the southern mid-latitudes. But interestingly, from a change perspective, what we're seeing is that in the southern hemisphere, there's a general drying with latitude, whereas in this northern hemisphere, northern mid-latitudes, there's maybe not so much of a change, and then maybe at higher latitudes, there's a slight wetting in annual total precipitation. But where these two regions are kind of symmetric with one another is in change in snowfall fraction when low to no snow emerges, and that kind of makes sense because we kind of isolated the warming levels when snow will considerably change in these two regions. And so to kind of translate this into a more nuts and bolts way for water managers, we also kind of showed the runoff efficiency changes between these regions. Runoff efficiency is just a really simple metric of how much runoff do you get for the total amount of precip that you get. And so it's a ratio from 0 to 1, 1 meaning all of your runoff or all of your precipitation is being translated into runoff. And so what's shown here is, again, the northern hemisphere in blue, southern hemisphere in green. And what you're seeing is that in both regions, runoff efficiency declines by about 8 to 9%, except in regions where you have, again, glaciers, like in the southern hemisphere, and what we think to be enhanced frequency of atmospheric rivers at around 32 degrees north in the southern hemisphere. But on the net, both regions show a net decline in runoff efficiency as a result of low to no snow, which makes sense because snow is a more efficient runoff generator than, say, rainfall is due to losses through evaporation or whatnot. And so to show this in kind of a map sense for runoff efficiency perspective, we also put together these diagrams where we're showing the historical runoff efficiency between these two regions from 1950 to 2000. So again, 0 to 1. And then these are the change in runoff efficiency, essentially when you get to low to no snow in the 2070s to 2100s. And again, it's just kind of saying what I mentioned earlier, but in a spatial sense, where runoff efficiency declines predominantly throughout much of the Western US into the Northern Rockies, especially in the continental kind of regions of the American Cordillera. Whereas in Chile, it's similar story, except for maybe in the northern part of the Chilean Andes and into Peru, where you might have enhanced atmospheric river activity, and then also regions where you have glacial melt that's changing runoff efficiency. And then we, did the whole, what if you held dry years only or wet years only, to kind of see like, well, what if you get an extreme wet year? How will that change the runoff efficiency in the model world? And again, it's a similar story that predominantly throughout the northern and southern mid-latitudes of the American Cordillera, that runoff efficiency declines in both wet and dry years. There are some regions where you might see slight increase in runoff efficiency, maybe due to atmospheric river changes in atmospheric river character activity. But on the whole, it'll be about an 8 to 10% decline in runoff efficiency if we reach this warming level and kind of snow changes in the way that the models project. And so I just wanted to say that in order to prevent low to no snow in either hemisphere, we identified that the global warming level would need to be held at most 2.5 degrees, and that's predominantly to keep low to no snow from emerging in the southern hemisphere more so than northern. And then to just put this into context that, this isn't set in stone. This is also just, a model estimate of what's to come. And a lot of these model estimates that I use, because they have limited computational power, they assume the RCP 8.5 scenario or the high emission scenario. And so that's kind of why we also try to use the warming level analysis to get around that. But in order to keep ourselves from, say, a 1.5 degree future, the carbon budget on the right here is being shown, and we've essentially almost used up all of our carbon budget to exceed the 1.5 degrees of warming, but we could still potentially prevent this 2.5 degrees of warming that would lead to low to no snow. And just to put this simulation into context, I helped a colleague of mine, JP O'Brien, with the Pacific Crest Trail, put together its first newsletter on climate change. And so we use this model run to kind of convey to PCTers what change might look like from a snowpack perspective on trail conditions. And so on the left here is just an animation stepping through 20-year periods from the historical through end century. And so, in the 1960s, 80s, 2020s, the March 1st to July 1st snow order equivalents are pretty abundant. However, by the mid-century and end century, you start to see considerable declines, particularly in places like the Cascades and northern part of the Sierra Nevada. But I encourage you to read this little article. I think it was really nice that the PCT finally is recognizing climate change and kind of getting out to their community. And then, I just wanted to highlight again that this warming level is not set in stone, and there's things that we can do about it to preserve American Cordillera's ability to kind of maintain historically expected seasonal snowpacks. I think there's this really nice carbon brief article here on the left, which shows kind of the IPCC scenarios used by the models and their estimated levels of warming on average. So again, that SSP 585 or RCP 8.5 scenario used in a lot of the model runs that I showed you earlier, it's assuming about a 4.7 degrees of warming. I think a lot of climate scientists will say that we're maybe more in these two IPCC scenario, 2.7 to 3.9. And that pans out with what our current policies are projected to get us to globally at about 2.6 to 2.7 degrees of warming. If we were to kind of commit at Glasgow to our 2030 commitments, maybe we could have kept it to 2.4 degrees. And if we do all the right things at all the right times, we can maybe limit to 1.8 degrees of warming. But that requires a lot of urgency and action. But there's work here at Berkeley Lab on a blueprint on how we get to that net zero promise at 1.8 degrees. But that 1.8 degrees, potentially or hopefully will keep us below this 2.5 degrees of warming. When we get to current policies, we're at or near that or right now. So it's kind of worrisome, but just wanted to highlight that, hope there is some hope that we can still prevent this future from occurring. And there are blueprints available. And this is just one of them at Berkeley Lab, but there are others as well. And then just to set in context here that, I was talking a lot about mean changes in snowpack. But even with present warming, we're having these anomalous heat wave events, for example. And so in 2021, there was the Pacific Northwest heat wave. And what was remarkable is that the Mount Rainier snowpack shown on the left before and after the event. And then this is a webcam showing Mount Rainier in the distance. And then just a slope probably here on the left, where in the matter of weeks or a week, 30% of Mount Rainier snowpack was lost. And so there's questions on, was that water lost to the atmosphere through evaporation? Was it lost to drier soils? And, will this become a more common occurrence in the future? So I'm hoping to get into that style of work in my Cascade project in the coming months. But just to put in context that even with current warming levels, we can get these dramatic changes in snowpack with, say, heat wave events. And then just to highlight that, again, managing water in Chile is even harder, I would say, than in the Western United States, and they have significantly less built infrastructure and ways to mitigate low to no snow future, and they might face it at an earlier time than in the Western US. I just want to highlight that already they're experiencing kind of drought conditions. So this is a photo taken in March 18th of 2022 of the Valparaiso region. Basically, this reservoir usually has about 38,000 Olympic-sized swimming pools, but only about 2 pools worth now remains. And Valparaiso is pretty close to Santiago, which is again, where about a third of the country's population lives. And so the government kind of estimates the country's water availability has dropped about 10 to 37% over the last 30 years and could drop another 50% by 2060. And currently the best strategy that I've seen that they employ in Chile is to truck water from places where they have it to other places where they don't, which costs a lot of money. And so there's this study on the right here by Renee Garode that highlights the cost of moving water when it's needed during drought conditions. And in 2015, when they had a really water supply challenge here, it cost about $45 million to truck that water where and when it's needed. So significant costs associated with that. But I think there's some really promising science-based solutions that could be a part of, maybe not completely offsetting low to no snow or snow loss heading into the future, but could be ways to blunt the impacts felt by it. And so I think things like manage aquifer recharge, forecast informed reservoir operation, and getting better with remote sensing-based water budget monitoring techniques can really help us to understand how much water we have available in the system, maybe manage our water infrastructure in a more day-to-day versus month-to-month kind of perspective, and then move that water where and when it's needed to places where we could store it in a natural sense in the aquifer, rather than say a snow or release it and quote unquote lose it to the ocean or something like that through managed aquifer recharge. So I think these are really exciting opportunities, and I'm sure many of you in the watershed SFA are looking into this. But yeah, again, I hope there's some hope on this low to no snow kind of future perspective. But just to kind of finish off with a summary slide here. So the hydroclimates in the mid-latitudes, American Cordillera, become even more distorted mirror images with warming due to differences in hypsometry and dynamical and thermodynamical changes with warming. Widespread and persistent low to no snow emergence in the southern mid-latitudes American Cordillera occur about 20 years earlier in the 2050s versus 2070s at 1/3 of the local warming level. And it results in runoff efficiency declines of about 8% on average in both dry and wet years. So that will even stress water management infrastructure even more, because even with as much precipitation as historical, you might expect 10% less of that being translated into actual runoff into reservoirs. And then a prevention of a low to no snow future in either hemisphere requires that global warming be held to at most 2.5 degrees of warming. And just to highlight that, the southern Chilean Andes have the highest global water tower index outside of Asia. I mentioned the Merziel paper at the beginning of my talk here, yet have significantly less built infrastructure, monitoring networks, and forecasting centers than the mountainous Western US or Western US in general. So there's kind of a climate equity aspect to this work too, and hope that we can share best practices amongst one another between Chile, California, and the Western US. And I again encourage you to kind of read the paper, and I'm happy to take any questions or your emails as well. So thanks, Ken.
Brilliant. Thanks so much. Gosh darn, that was just an outstanding and comprehensive presentation. Thoroughly enjoyed it. I don't know if others have actually utilized these QR code links in their own presentations. I have not. In fact, I haven't even seen it before, but I really commend you to that. And I'll certainly be bringing it into my future talks and presentations. That was just outstanding. So Alan, if you wouldn't mind unsharing your screen so we can see faces and start taking some questions. Specific questions for Alan. Dan.
Alan, yeah, thanks for a great talk. I really thoroughly enjoyed what you presented. Didn't want to talk or just ask a little bit about atmospheric the current state of atmospheric river forecasting in the southern hemisphere, what that looks like, and if you could talk just a little bit about kind of the sort of the meteorology of them. We sort of get a lot of information here in California about pineapple expresses and things like that, and just wanted to understand if it's a kind of a similar story, and if we have kind of that level of predictability on the sort of the shorter timescales right now, and sort of that level of meteorological understanding of those rivers right now in the southern hemisphere.
Yeah, so from what I've heard from Chilean colleagues is that there's not a lot of radars throughout the country, and there's slowly but surely building up kind of a forecasting center focused on atmospheric rivers. And I think they're learning a lot from the CW3E at the Scripps Institution of Oceanography and a sharing of information there. But I believe the group that's out of the Universidad de Chile is called CR2. I think you can feel the exchange maybe there with CW3E and CR2, but CR2 is kind of the group that is doing forecasting for atmospheric rivers and doing more of the impacts analysis associated with atmospheric rivers. So I'd point you to CR2 and Universidad de Chile for more information on that. And Rene Gouraud, it was mispronounced his last name, but he's pretty prolific, and he has his hands all over the AR literature for South America too. So I'd recommend reading his work. And Maximili Viale as well comes to mind.
Thanks, Alan.
Yeah, thanks for the question.
I've got a question for you. Actually, it's a kind of a two-parter. The first is, can you talk a little bit about what the translocational effects are between, these obligately sort of coastal arrivals of atmospheric rivers as they propagate, westward and start translocating kind of the precipitation effects to, more of the critical mountain ranges in the inlands, the Wasatch Range, for instance, or the Southern Rockies, in terms of feeding stream flow for those reservoirs you alluded to in the Upper Colorado River Basin. So what does that look like? And is that, sort of food for future research?
Yeah, I mean, in a warmer world where, these ARs could be supercharged, especially the Cat 4 or 5, you might expect their inland penetration potential could also change. But I don't think there's been too much area of study on that, other than maybe linking ARs with, say, avalanche events in the interior, portions of the Western United States. But yeah, I think that as the world continues to warm and these ARs get a little bit supercharged, I think that'll be definitely something to continue to monitor.
Yeah, thanks much. And so kind of related to that, the second part question, given what you've shown us today, what's next? What are the next big questions tied to this research that you're going to be pursuing? Yeah,
I probably came across that I was hedging the results a little bit because it is a single model result, and it is at 20-kilometer resolution, as many on this call know. Maybe that's too coarse to get it, more local scale information. So again, I guess I'll do the age-old thing that modelers do, is like, we need higher resolution, we need more ensemble members, we need more models to contribute data that we can do this analysis again. But I think the proof of concept framework hopefully could be reapplied. And I've heard from colleagues in the Alps and in the Alps that would like to see some of this work done there as well, because they're experiencing, again, lowest snow year on record currently, and they've also faced some snow and ice eater heat waves in recent years where there's been considerable glacier loss. So I think, yeah, maybe trying to apply this work in other regions and more comprehensively across different approaches, that might be something to pursue. Cool, and that heat wave, snow relationship, I think, is something I'm really interested in the coming years.
Dan, did you have a follow-up?
I did. I'm going to ask a somewhat pointed question of you, Alan, based on that last point. Can you opine about whether you think higher resolution and more models, what will be learned from higher resolution and more models? And if you given that you did a thermodynamical analysis and hypsometric analysis, which one might expect something the models should be sort of getting, rather than rather than sort of looking to maybe just higher resolution and more models. I'm curious your thoughts on that, and sorry if it's a little bit too pointed, but we've seen a lot of.
That's fine. So my other hat that I wear a lot in my analysis is using these variable resolution approaches, where you can do hyper-focused telescoping resolution over a given mountain region. And so what I've found is that resolution isn't always the panacea, right? Like, our parameterizations, the models are built for coarser degree runs. And as you push that resolution down, it doesn't necessarily make the water year look better from a precip or snow perspective. But what I'll say is that from a physics perspective, I think that higher resolution might get you a better rain snow transition line. You might get, a more conservative estimate of low to no snow in the future, because you might be able to see higher, elevational snowpacks building and being maintained for longer periods of time at higher resolution. And then working at kind of the local scales that water managers need, you can maybe get a better estimate of runoff efficiency in a given basin or something like that. So I think there's a lot of really important details that need to be fleshed out. But at the moment, tried to just analyze American Cordillera wide on purpose, in a way, because we felt like the model was fit for purpose for that scale of analysis. But yeah.
Thanks.
Yeah, hopefully that answers your question. Yep.
Will, you have a question?
Awesome. Yeah, thank you, Alan. I guess sort of following up on the last one a little bit. I guess, yeah, in those like high res MIP model runs, yeah, I mean, so we expect warming, and when from the like Clausius clap around, more moist ARs. But I guess, do you see in the model results, do you see like, you see presumably more rain, the rain snow transition moving up, but do you also actually see areas where you get more snow accumulation at like the highest elevations? Is that something you found or?
Yeah,
can it
so
happen?
we kind of, in this paper, at least, we've kind of done it at the annual scale, right? But what would be interesting is maybe use these models to look at subannual and kind of look at, do you know, around mid-century where the atmospheric river is a little bit amped up, but can still produce a lot of snowfall, do you get these extreme snowfall events occurring? Yeah, I think that's a really interesting thing to take a look at. And I'm sure there's folks working on that right now, but not a lot come to mind.
Awesome, thanks.
Great. Time for another question or two, if folks have them. Otherwise, let's thank Alan, and we'll be sure to get him back on the 2-year invite schedule again. So 2 years from now, we'll see what other great things that Alan's got to share with us. But that was outstanding, comprehensive, and really fascinating. So thanks again, Alan. Really appreciate your time today. Thanks everyone for joining us. Again, we're on our bi-monthly schedule, so we'll be touching base again in May. The hope, actually, we're potentially going to be hearing from talks from Sarah Tessendorf in May, really looking at the potential for weather modification and cloud seeding in the Upper Gunnison River. That's work that's being supported by the Bureau of Rec, and how that information is being incorporated in forecast models. So sort of staying with this general theme, but now sort of looking at additional mechanisms that we as humans may or may not have to actually increase our snowfall totals, even by 1 to 2 to perhaps as much as 5%. We shall see. So anyway, thanks. Thanks for the time today, and we'll see you all in 2 months. And thanks again, Alan. Great to see you.
See you later.